So now let's talk about graphs. And the reason we want to dive into graphs before we do really anything else is that a statistician's best tool is to really visualize and understand their data before they start digging. And so graphs are a great way for us to do that. So what we're going to want to do is look at the pattern of scores and see if anything jumps out at us that we should be noticing. So graphs often make it easier for us to see certain patterns, certain characteristics or trends. And so what we want to do is talk about the different kinds of charts or graphs to do for the different types of data. So our first type of data will be quantitative data. And so we're going to look at the different kinds of charts we can make or graphs we can make for those. So the first one would be a stem and leaf display or a stem and leaf plot, then a histogram, then a frequency polygon. So this is our to-do list for how to look at quantitative data. Then for qualitative data, we're going to look at bar charts and pie charts. Now, it's important to remember that quantitative data are for numbers and qualitative data are for classes or categories. So these are things that are words. So this is our to-do list, and we're going to see if we can figure out how to make graphs to visualize these type of data. So let's first start with stem and leaf displays. So if you see this data set, it's raw data. Let's say it's just we asked people about dollars in their pocket. And you can see that it's kind of boring. It's not even in order. It's hard to visualize any of the patterns that might emerge there. So we want to start with this very first approach, a very easy, simple approach at visualizing our data. So what you see here is up here I have copy and pasted that raw data, and then I just took the first row up here and I pasted it here. So we're going to just break apart this first row. And so we're going to make stem and leaf of each of these numbers. And you can think of it like a plant. The stem is the primary part and then the leaf is the kind of the hanging part. So we'll have the tens unit be our stems and the leaves be our ones unit. So let's take these first numbers. Here we have 14 and 15. They're both in the tens with a 1 of 4 and a 1 of 5. So those are both tens. So we're going to take this 4 and this 5 and put it in the leaves. So this is telling us 14, 15. Then we're going to take the 20s, and we see that we have two 24s. And so we're going to put those 4s here. So what I want to point out is that what this is saying is 24, 24. So these are the 10s, these are the 20s. The computer's trying to move on without me, so I apologize if that keeps happening. These are the 20s, so this is 24, 24. Now let's do the 30s. So we have 36, 35, 35, and 33. So now let's put that down as a leaf. And you can see that this is coming as 33, 35, 35, 36. That's a different order than what we saw the data appear up in this line. And that's because it's important to remember that the data need to come through in order. It makes more sense for them to be in order here so we can visualize the patterns. So this would be 33, 35, and then this last one would be 36. So you don't want to put them in order that you see them. You want to put them in order in the numerical order on the leaf. Now let's do the 40s. Do you see anything in the 40s up here? No. But should we just remove this line altogether and say there's no 40s? Well, that doesn't make sense either, because 40 is still, the fact that there are no 40s is still interesting to us. So we want to put this 4 here, and then should we put a 0 so we can indicate that there were no numbers in the 40s? Well, that would be wrong too, because that would tell us that we saw a number 40, and we didn't get anything in the 40s. So what we'll do is we'll just leave this 4 here, and then move on to the next. So here we see there's a 52, so we're going to put 52. And so that tells us here that there's nothing in the 40s, but we have a 52. So this is, no data is just as interesting as actual data. So this number here is interesting to me as a statistician, that nobody had any $40 bills or anything, or of course nobody had a $40 bill, but nobody had $40 in their wallet. So now we'll do the 70, and we see that there's 73. So for just this first line up here, what we see is that this is our stem and leaf plot. Now let's look at it for the entire data set. So this is the entire data set, and you can see here we have a much more fleshed out stem and leaf plot, and we can look at different numbers that we didn't see on that first line. For example, we have 64, and 66 and 67, and those come down here, 64, 66, 67. Notice that we had a number 9, and so the leaf for number 9 would be 0, because that means that there was no tens units. All right, so what I wanted to point out is that this is a very simplistic way of visualizing our data, but we can already see patterns where numbers are very popular, where numbers are not very popular, and this is a great way for us to kind of start to visualize what's happening. Let's say we have a data set like this. It's really large, and oh, these numbers are messed up over here. I apologize. But still, it's very difficult to make sense of what this data set is saying. So let me turn this into a stem and leaf plot for you. So if I turn this into a stem and leaf plot, that's a little bit easier to see the pattern. You can see the 70s are very popular, right? And then we can make sense of, or at least start to see what are the most common numbers and the patterns. When I see something like this, though, what I tend to do is turn my head to kind of visualize it. Wow, I didn't know it would do that. So if we turn our head to the right, we kind of see a bar chart. And so when we look at it, it kind of looks like a sideways bar chart. So that's going to be our next approach. So we've already just covered stem and leaf plot. Now let's look at how we can turn these data into something with bars in them. So this is a histogram. These are the same numbers we just saw, but in a histogram form. I just asked Excel to make a histogram for me, and then I didn't tell it anything. It just churned this out. So what I wanted you to notice is that these bars look a lot like the bars we saw with the stem and leaf plot. The only thing that's different is that rather than have each of the tens unit be their own bar, they've kind of broken it up. And that's because Excel said, you know, these bin ranges seem to be broken up more because there's a lot in the 70s. And so rather than go from 70 to 79, we'll go 70, 74, 75 to 79. And so what we can see is this is a very visually pleasing way of looking at the data. Now you'll notice that we have these x-axis and y-axis labels. And so what this x-axis label is saying is this is the range of scores, right? For we have starting at 35 and ending at 99. And then this is the count. So for example, if I look at the 50 to 54 range, I can see over here it says there's about 7. And so this bar is pushing up to about the 7 marker. So this is important because this lets us visualize the pattern of data and see kind of where the height of each bar indicates to us how frequent that item is. So let's talk about the properties of a histogram then. What a histogram is, it's a number of bars placed side by side. So that's kind of the definition of them. The width of each bar indicates the interval size. So if you have a histogram where the range is very small, like it's only 5 points, then you don't need to have a really fat bar. But let's say it's $100 difference between one bar to another bar, then you should probably have a fat bar to remind your readers that this is a range that has a large number of intervals in between. And then by definition, the height of each bar is the count of how many numbers fit in that range. And we saw that when we're looking at 57. And then a big piece of the histogram, the part that differentiates a histogram from a normal bar chart, is that there are no gaps between the bars. You notice those bars were touching. So histograms, the bars touch. And that's to remind our readers that the numbers that we're looking at are continuous in nature. So quantitative data are numbers. And we want to remind our readers when they're looking at the charts that these numbers really indicate you can move from one to the other. Unlike qualitative data, like if I had been looking at the count of different religions, people don't tend to move from one religion to another. So I might put a gap between the different kinds of religions to remind my readers that that tends not to happen. But if I'm looking at dollar amounts in your pocket, these are numbers. Numbers are continuous in nature, and so we put the bars next to each other to remind our readers. So you're always trying to help readers read your charts, and putting those bars side by side can help them visualize that. So here's a couple examples of histograms. This was a very famous one in 1997 by Cohen and Rotten. And so what they were looking at is with increasing temperature amounts. So here they have the temperature ranges on the bottom, and then they have an index of assaults over here on the y-axis. That means they're just counting assaults. It's not just a straight count, though, because you know, New York is so much more populated, they would have to have kind of a ratio of assaults to how many people live there. And so what you can see is there's an increasing trend. The hotter it gets, the more assaults there are, and then it starts to taper off. There's several things I love about this chart and some things I don't. I love that the authors put this point here. They're really helping their readers understand what's happening. So they say, hey, by the way, aggression rises to this point and then decreases. I mean, it really can't be any more clear to the reader what the message is that's trying to be conveyed. The one thing a couple things I don't like is, notice that they put the numbers in the chart here. So this is the 5, this is the 5.1. I feel like that clutters the view, and really I should be looking at the bars and not being distracted. If I really wanted to know that was a 5, I could take a ruler and look and see which number it lines up with over here. So it's not really necessary, and I feel like it clutters the visual field. We really want the data to be speaking for themselves. The other thing I don't like is, notice there's a blue bar and an orange bar and a blue bar and an orange bar. And you might look at that and go, oh, what's the difference between the blue bars and the orange bars? And actually here they convey nothing. They're just trying to be cute, like hot, cold. And that's not ideal. You want your bars, if they're different colors, to indicate different things, like perhaps these were males and these were females or something like that. But in this case, with this histogram, the blue bars were just cutesy and the orange bars were cute. They weren't defining a different category. So you want to save differentiating your bars for something of meaning. So here's the common shape we have of histograms. The first one we call it a normal distribution. It's so important to statistics that we have an entire week to discuss the normal distribution. But you'll kind of see it's kind of a mountain curve to it. Then we have a bimodal distribution. Now I haven't taught you what a mode is yet, but bimodal means there's two of them. You might be able to guess what a mode is. And in this case, a mode is like the peak of the distribution. So you see how there's two of them. Often we see distributions that are bimodal. Let's say I was collecting data and, I don't know, let's say I was looking at all students in my stats classes, and I collected all their data and how they did on the test. And then when I plotted it out, I see this distribution like this. And then when I start to look at the students, perhaps, wow, these are all the students who did the homework, and these are the students who skipped the homework, right? I don't know what the premise might be, but what if I plot the data as they are in their kind of raw format, I might find there seems to be two patterns that emerge, and then as a statistician, I'm going to want to go further and figure out what is differentiating those two groups. And then down on the bottom here, we have skewed distributions. This one's called a negative skew, and this one's called a positive skew. These are so impactful for statistics. I want to take a slide just to talk about those in themselves. So for skewed distributions, if we have something that's being measured, sometimes the data naturally appear in this way where they have an upper or lower limit. So the negative skewed, which is over here on the left, we say it's skewed to the left. It's a negative skew. It's what happens when we have what we call a ceiling effect. So you can't score any higher. Let's say I gave you a pop quiz on graphs, and everybody did really, really well because it was such an easy lecture. And so what happens is I should have made the test harder. If I really wanted to differentiate A students from B students from C students, I should have made the test just a smidge harder so that I could pull this upper limit out. So everybody kind of just smashed to the top. Everybody scored really well. And so I should have made a few extra harder questions to kind of really pull the tail down. And so that would be something that we would see if we had a negative skew. On the other hand, a positive skew would kind of be the other way. That would be like if I gave you the final right now, and it's so difficult because you haven't had any of the material, we would say that it's the floor effect. It was so hard, everybody hit the floor. So you can see that everybody failed that test. Everybody failed that test. And so there's very few people who maybe guessed and did really well, but everybody else is down here. So what we say is that it was so hard that you kind of hit the floor. Now, both of these are not ideal for statisticians. However, I think students would be more likely to hate this one than this one because that means nobody did very well. But when we're looking at these type of data, They can be problematic for us in future interpretations, which we'll get to in a future lecture. But so it's important for us to identify positive and negative skews. So one thing I will do is I'll teach you why it's called a positive negative skew in the next lectures, but I want you to be able to identify it. So if you think about a skier, not a base jumper, but a skier, if you were going to ski down this hill, you'll see how this skier is skiing off into the negative numbers, and this skier is skiing into the positive numbers. And so that's one trick to help you remember whether it's a negative or positive skew, because students often mix them up because they think, oh, this one, everybody's on the positive angle, it must be a positive skew. But actually, it's the skew is where the tail of the distribution is. And so this skier is skiing off into the negative numbers, so it's a negative skew. This skier is skiing off into the positive numbers. The last quantitative graph I want to show you is called a frequency polygon. So if we had a histogram like we have here, what we would typically just do is draw a dot at the middle of each bar and then connect the dots like you see here. It's really not adding a whole lot to your discussion or your visualization, but sometimes people like to see the line because, again, the line reminds you it's continuous in nature rather than the bars. And the line also kind of helps you visualize, where would it be if we had had a bin that was halfway between this one and this one? And so you can see in this line, no, we would guess it would be right about here. Now, if you wanted to leave it as a histogram and that area mattered, just make your bin smaller. So frequency polygons aren't too complicated. They're just making those histograms into a line chart so you can visualize it. All right, just a little bit left to go. You can do it. So now I'm going to talk about data graphs for qualitative data. And the first technique is a bar graph. Now, you might be confused because the histogram had bars in it. So actually, by definition, a histogram is a bar graph, but it's a special kind of bar graph. It's a bar graph used for quantitative data. So the other kinds of bar graphs that aren't the special kind, those can be used for qualitative data. So unlike a histogram, the bars don't touch. And that's, again, to remind our readers that there's discontinuous nature of our data, that we don't move from one category to another, that they're really separated. So here's an example of a bar graph. This was a motivation of reported hate crime. Notice that they didn't label their axes. That's not ideal. But we can see that race had a very high number of motivation for hate crime, and then it drops off. But there still counts for religion, sexual ethnicity, and then they have a catch-all. So remember when we were talking about our lists of responses, we had mutually exclusive and exhaustive. This list is mutually exclusive and exhaustive, which means if your motivation for hate crime was race, then it can't also be religion. That's mutually exclusive. And it's exhaustive because they have every possible motivation for hate crime because they captured the others here in the unknown. So you'll notice that they put a gap here between the different bars. And that's really important for us because it reminds us that, you don't move from one to the other. It didn't really have to be that race came first in this bar graph. It could have started and then went alphabetical. So it could have started with ethnicity. And so by putting the bars in this order, we put a gap between them to remind our reader they didn't have to be in this order, but the author kind of thought, hey, let's do it in descending order and then just put unknown at the end. Now you'll notice also there's a couple other things they did that I don't like in this graph, and this is really just stylistic, but notice they left this thing here said number. I mean, that's not necessary. That's clearly what this bar is indicating, so that piece didn't need to be there. You can also notice that they put kind of a box around the top and the side here of the graph. Now, I like there to be a line on the y-axis and the x-axis, but I'm not a big fan of putting the box around. And really that's because, again, you have to help your readers read this. And by putting a box around it, you've kind of accidentally suggested to your readers, this is all that there is. So by putting an end cap here, you're suggesting there's no other reason for hate crime. Now, I know you have the label here of unknown, but you want to leave it open and remind them there could be other things I haven't assessed. The other thing is by putting a line across the top, you're suggesting to your readers that there could not be any more hate crimes. So this is the cap. They don't go any higher, and you don't know that. So leave that line off to remind your readers that in the future, this number may get higher. But this is a great example of a bar graph. Now, what makes it a bar graph is that there are bars. It is not a histogram because these are not quantitative. These are not numbers. And so we put gaps in between. So if I were to ask you to identify a bar graph versus a histogram, by the way, a histogram is a bar graph. But if I asked you if this is a histogram, you would say no, because the bars aren't touching. Now we're going to talk about pie graphs. Pie graphs are rarely used in academic or journal articles, but they can be helpful. I'm more of a fan of bar graphs, but if you're trying to account for 100% of your data, pie graphs or pie charts, I kind of use them interchangeably, they can be good because you can see here, this is 100% of something, and then these are the categories A, B, C, D. Now, if I asked you what percent of people got an E, you may not have even noticed there was no E in this pie graph until I asked you to look for it. And so that's one of the reasons I don't like pie graphs is there may be something that was measured, but because nobody responded, it's not going to show up in the pie graph, but it would show up in the bar chart because you just would have, you'd have the category E and then no bar there. However, this makes more sense because these are letter grades, right? The number of students who got an A, B, C, D, F. So if you're trying to account for 100% of the students, where did their grades go, this was useful. But it isn't the only way of visualizing data, and sometimes a bar graph is more meaningful. So you want to make sure that you understand what you're trying to convey and use the appropriate chart. But if the goal is to account for 100% of something, a pie graph would be the best way to go. That's why accountants often use pie graphs, because they have to go, where did all the money go? So that's why you see that more with them or with voting blocks or those kinds of stories. I just want to talk a minute about misleading graphs before we end. Graphs can be presented in a way that's misleading, and I want you to identify when that happens so that you're not tricked. So these two charts are showing the same data, but it really depends on how you're looking at it, what your interpretation would be. So this is saying university administration's salary. And so that university administration, those are like the presidents, the vice presidents, the deans, that kind of thing. And so if you're looking at these charts, you can see that on this chart, it looks like they're making more and more each year, where on this chart, it looks like they're making roughly the same amount each year. Can you identify what the key thing is that makes the left chart different from the right chart? So hopefully you saw it was this, that on the left chart, it starts at 30. So you see this little squiggly line? That's the line that we use to indicate that we have not started at 0. So it's kind of like you zoomed in. And when you zoom in, the little subtle differences that are over here really stand out over here. So I want to tell you when you're allowed to do this zooming in. If you find there is a statistically significant difference each year, which I haven't taught you how to do yet, but once we learn, if you find a statistically significant difference, you're allowed to zoom in. If you don't find a difference among the years, then you won't zoom in and you'd have to do this. Well, let's pause and think for a minute. If you're looking at a peer-reviewed journal, are you likely to see a chart like this? I really want you to think about where I'm going here and try to guess. If you're looking at an academic journal, are you likely to see a chart like this? Okay, I'm going to give you the answer, so if you're not ready, pause it so you can try and come up with it yourself. Okay, the answer is no. Why would I not likely see a chart like this? Because remember, journal articles are only publishing where we find significant differences. So you're likely to see a chart like this in the journal because we found a significant difference. If you found no difference, you won't be publishing, so you're not going to read it. Something to keep in mind. Now, that's the rule for academic journals, but if you're looking at magazines, newspapers, news stations, they can do whatever they want. And they often will choose the picture that best sells the message they want. So you have to be keen on looking at the picture and what you're trying to get from it. All right, I just had another example. So here was a paper published that looked at mean happiness scores, and boy, it looks dramatic, like our mean happiness scores have really dropped over the last few years. But actually, because they start, and look at this is on a scale of, I think it's a scale of 0 to 5 actually, but it just goes from 2 to 2.10. So they really zoomed in. So if you look at the data and you pull back to starting at 0, you can see there's really no difference in happiness scores over the last few years. So again, you really want to be aware of what the message is that the graph's trying to convey and not be tricked, unless they did find a significant difference here. But then that would imply that their significant difference is based on a 0.05 point difference. Oh, and here's some others I found on the internet. They're kind of fun to look at. I'll just put them all up here. Like this one I think is interesting. They were looking at what people would indicate for their opinions, and you can see 70%, 60%, and 63%. So here, that clearly is over 100%. That's not possible. And then if you look at this, you can see that they're using a bar chart. Now, it's not, the error is not so much that they had a picture in here, but if you're looking at this picture, this actually sums up to be more than 100%. So that is a little misleading the way they've put these numbers there. It makes it look like injuries are happening at an astronomical rate, but it's actually saying of the injuries that have already happened, what of them are thigh bone, that kind of thing. And then this picture here is a little bit strange and misleading. So for example, I just want to point out that this 8.8%, see how it's the dip? But this is an 8.6, which technically should be lower than 8.8, but it is higher. So these charts can be misleading. There's something you just want to look closer, especially if it's not in an academic journal. There may be an attempt to convey information, and they don't necessarily are malicious, but you want to just make sure that you're understanding what they're trying to convey, because not everybody's had to take a stats class before they can generate these kinds of pictures. All right, so that's graphs. Well done, you've done it. I look forward to moving forward with you to do more descriptive statistics so we can really visualize and understand our data. Oh, sorry, wait for me. I'm trying to turn it off.